We're going to be looking now at the notion that two graphs are not the same. Recall that isomorphism means that two graphs are the same. They might look a little different at the start, but if you go through a process of sort of moving things around, you can make the first graph look like the second graph. Non-isomorphism is the case where that is not possible. And I have an example on the screen here, G and H. They have a lot in common, but they also have some differences. So I'm going to describe a process that is helpful for determining if graphs are not isomorphic. In some cases, it gives you an answer quickly. In some cases, it does not. In the example here, it's going to be a little bit challenging to show they're not isomorphic. So just to have a second example that is easier to follow, I'm going to throw in a simpler figure. Let's call these G1 and H1. G1 will have 3 points in a nice line. H1 will have 3 points with an extra bit crossing. Okay, so if we look at these new figures, and I were to ask you, how do you know they're different? There's lots of possible answers, and one of them might be, well, G1 has 2 edges, and H1 has 3. So in order to show things are not isomorphic, a good starting point will be to compare the sizes. Of the two graphs, oftentimes called G and H. Now, what does size mean? Well, there's actually 2 components to size. First, count the number of vertices. Then, count the number of edges. And recall that that absolute value sign is called cardinality, and it means how many objects are in that set. So if the number of vertices and the number of edges are the same, then in a sense, they have the same size. So in this particular example, let's say we're looking at G, the number of vertices in graph G was 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the number of vertices in graph H, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's again 9. So far they're the same. The number of edges in graph G, 1, 2, 3, 4, 5, 6, 7, 8. And then the number of edges in graph H, 1, 2, 3, 4, 5, 6, 7, 8. Again, 8. So for G and H, their sizes are the same. Now, what about in the second one we're looking at here? In this case, when I compare the sizes, I will first have the number of vertices. So the number of vertices in G1, 1, 2, 3. And the number of vertices in H1 was also 3. Then the number of edges in G1, 1, 2 edges. And the number of edges in H1, 1, 2, 3. And in this case, they were different. Well, if they're not the same, they're different sizes, so they can't be the same. It's like saying, if a student in this class is 5 feet tall and a student in this class is 6 feet tall, they can't be the same student. So 2 different sizes, not the same, and that would mean not isomorphic. So that's the lucky case that we're all done after one step. So let's go back to the unlucky case. On the left-hand side, the sizes were the same. The next thing that you should compare is called the degree sequences. The degree sequence is what you get if you write all the degrees and then you sort them from smallest to largest. So in G, the degree of A is 1, B is 1, C is 1, D is 1. There's only one edge. E has 3 edges. F has 4. G has 3. H has 1. And I has 1. And then when I sort it, then I had 6 ones and 2 3s and a 4. So if you do not do the sorting step, your comparison won't work. Now let's say I look at H. I'll do the same process. 1, 1, 1, 1, like that. And then T was 3, U was 3, V was 4, W and X are 1. And then I sort. Well, this has 6 ones, 2 3s, and a 4. So the degree sequences are the same. So just looking at the degrees, that you can't tell these apart. So I need something else. Okay, step 3. In step 3, there's not an obvious answer. So 1 and 2 are the really obvious things. You always should start with those. If it's passing, you have a dilemma. One thing is they might be the same thing. Another possibility is they're not the same graph. If you're not sure what the answer is, try something. Try another property or two. If you're still failing to find a difference, then start trying to pair things up. I am not going to try to pair them up here because it's going to fail. So I need something they differ by. Well, let's see, what do we have here? The most obvious difference visually is that in graph G, we had 3 at the end. Over here, we had 4 at the end. That's not a good enough answer. Because what does end mean? It might just be a consequence of the way I drew the figure. So when we talked about isomorphism, we talked about warping a figure to make it look very different. For example, this original figure and this final one don't really look the same, but they are. And so if you talk about a property and say something like the degree 1 went at the end, well, that doesn't mean anything in this version of it. So end is not something that has meaning on a graph. It's just a consequence of how you chose to draw it. Here it looks like there's an end point. Here there is not. Okay, so we can't say end. We need something else. Well, let's see. In this figure, I had degree 3, 4, and 3 again. So the 2 3s were next to the 4. Here, the 4 is only next to one of them. Now, this is a difference that has nothing to do with the way I drew it. It's just a fact. So a good option on the third step is often adjacency. Of different degrees. It could even be the same. So most often, the things you'll look for are different, but since they could be the same, I'll cross it out, but we'll kind of remember that possibility. So what I said earlier was in G, degree 4 is next to 2 degree 3s. In H, degree 4 is next to only 1. And I didn't write the 3 down. So in one of the figures, the degree 4 was next to 2 degree 3s. In the other figure, it was only next to 1 degree 3. That means they cannot be the same. So a proper approach like this will be pretty common. You don't have to do degrees at the end. There will be cases where that doesn't work, meaning I could have checked these adjacent degrees and found that they still matched up. Don't conclude they're isomorphic. To show they're isomorphic, you must actually pair up vertices. So I could check 5 properties and find they all agree, and the graphs might not even be the same. Just like you can find 2 people that agree in many characteristics, but they're not the same person. If they're both a male who is 6 feet high with brown hair and blue eyes, and somebody else is a male who is 6 feet tall with brown hair and blue eyes, that does not make them the same person. So at isomorphism, checking lots of properties, if they're all matching up, maybe it's isomorphic. You need to figure that out. But if you find one thing that they differ by, then it's not isomorphic.